Okay, now we're talking about Attwood's machine. An Attwood's machine is essentially a pulley like this with a radius r in which you have two weights hanging over it. You're going to have M1 and let's make M2 bigger. And what's going to happen is they're going to be hanging like this. Now, a couple things to understand it. First of all, that the tension is constant. So in any place I cut that cable, I'm going to have the same tension. So the T there and the T there are both going to be the same. They can't change. Second thing also, since they're connected, A is going to be constant. The acceleration is constant. Okay, so that's kind of important. That's the key thing to solving it. Now, this pulley is going to be a frictionless pulley. It's not going to add anything to the system. It's completely frictionless. It's not going to add any inertia to the system. We're going to completely ignore it in terms of solving it. Now, what this is going to allow us to do is then use Newton's second law and simultaneous equations to solve. Because up here, we have two unknowns. So in order to have two unknowns, I'm going to need two equations. And I'll get the two equations from my diagram. Okay, let's take a look at one. So let's redraw one here. Same thing we just had. I'll draw it smaller since I don't need the thing. I have M1 here. And I'm going to make M2 bigger. And I'm going to have to assume that this one is going to accelerate that way. This one is going to accelerate that way, and that's the key thing to solving it. I'm gonna treat that. Now, what I'm going to do is draw a free body diagram for each one. I draw a free body diagram for M1. It's going to look like this. Pulling down on this, I have M1 times G. Pulling up, I have tension. And I'm going to mark over here that it's going to accelerate that direction, so I know that I'm going to treat that as positive when I start trying to solve it. So these are my free body diagrams. Next thing I'm going to do is go for M2. Let's do M2 in a different color. M2 is bigger. M2. Down here I'm going to have M2G. Up here I'm going to have T. Core thing to realize that those are the same right there when you solve it. So let's do a Newton's second law for each one. So let's now say the sum of the forces on M2, and of course we're going to know that's equal to M times A, but let's go ahead and solve it. Now remember, we said that this one's going to go down, so I'm going to treat that as positive. I'm now going to go M2 times G minus T is equal to M2 times A, and I treat all of those as if they're positive values in the terms of this is positive value because A is going down, and I consider down to be positive. If I rearrange that and I move T to the other side, I get T is equal to M2G minus M1A. Now that's two unknowns in a single equation. I can't solve it. So now let's go to the second one. So now I'm going to sum the forces on mass 1. When I sum the forces on mass 1, now I have to remember that my A is positive going up. So now I'm going to write T minus M1G, because M1G is going down, is equal to M1 times A. And as long as I keep my things constant, I'm good. So therefore I'm going to get that T is equal to M1A plus M1G. All I did simply was move the M1G to the other side. Now, setting those two tensions equal to each other, I'm going to get M2G minus M1A, that came from that equation there, is equal to M1A plus M1G. This should be a 2. I look up at this equation right here. I made a slight math mistake. Okay, now I'm going to solve for A. So let's factor out A on both sides. When I move the A's together, I get M1A plus M2A. I move the M1G to the other side, I get M2G minus M1G when I move it to the other side. Okay, now factor out my A's. I get A times M1 plus M2. I'll factor out my G over here. G times M2 minus M1. Divide both sides by that. I get M1 plus M2 is equal to A. And there I have an equation that solves for A. So that's what it looks like. Okay, now if you then wanted to solve for tension, you can go back to either equation to solve for tension. Now, let's look at a shortcut. Like most things involved, there's sometimes an easier way to do it. So let's take a look at a shortcut now. One shortcut way of handling this is to simply do this. I'm still going to have M1. I'm going to still make M2 bigger. So therefore it stays with the same. You can make either one bigger, it really doesn't matter. But I'm still going to say that that's going to go up, that's going to go down. But now I'm going to consider my entire system together. So in other words, I'm going to put all of this together. Now, if I put all of this together, what I have acting outside of this is here I'm going to have M1G going down. Here I'm going to have M2G going down. Now I'm still going to look at my picture and decide that that's positive. So now what I'm going to do is the sum of the forces on my system. So I'm going to take all of those. Now I'm going to consider the positive ones first. Well, M2G is positive. This one is going opposite of that direction. So therefore I'm going to go minus M1G. That's equal to M times A. Now, in this case, your M times A is your entire system. So it's M1 plus M2 times A. So if I factor G out over here, I get G M2 minus M1 equals M1 plus M2 times A. Divide both sides. I get A is equal to G M2 minus M1 divided by M1 plus M2. Same equation I got a minute ago. Key thing to understand is the maximum acceleration I can ever have. What is it? 9.8 meters per second squared. So I'm always going to get a number between 0 and 9.8. Now let's try one with numbers. Let's do this. Let's make a quick one. Let's go 5 kg running over a pulley, and let's go 10 kg. And let's go ahead and let's go ahead and use our shortcut. And if we do our shortcut, I'm now going to say that okay, this is 50 newtons acting down, but the mass is going to accelerate up. Over here, I'm going to say that this is the direction of acceleration, and this is 100 newtons. So when I do my sum of the forces on the system, I'm going to say 100 newtons minus 50 newtons is equal to the total mass, 15 kilograms, times A. Well, this is 50 newtons divided by 15 kilograms is going to equal A. So A is 3.3 meters per second squared. Okay, now let's take a look at and calculate T. Now to calculate T, we're going to only look at one box. And in this case, it really doesn't matter which box we use. Let's look at the 10 kilogram box. I'm now going to say the sum of the forces on the 10 kilogram box. So now, again, Down is positive because I guessed which way the thing went. I'm going to say 100 newtons, which is down, minus T, which would be up. Remember, if I do a free body diagram, I would have this. I'd have 100 newtons down. I'd have T going up. My A is 3.3 meters per second squared in that direction. That's equal to 10 kilograms times 3.3 meters per second squared. So when I move T to the other side, to make it a positive value, I'm going to get 100 newtons minus, this becomes 10 times 3.3, which is 33 newtons. T is equal to 67 newtons. That's it. Hope that helped. We'll play with some more in class.